All right. So yes, my name is Nicolas Leblond, Tessent Field Application Engineer since a couple of years now, and I'm working with STMicro. So today I'm representing Sara. Actually, Sara could not join, unfortunately. We will miss her. She's a very good presenter, and so just to present this presentation, by the way, will be short. That way, we'll not fall asleep. And it will not be as advanced as what we've just seen. I think we're going back to the basics here, but that's always good for everyone. So Sara has been working on the evaluation of different EDT insertion strategies, just in the matter of trying to improve the coverage area, as I will introduce. So let's dive into the topic. This is the agenda. We are first going to present the ST imaging division. It's a very important division in STMicro. We'll then talk a little bit about the project constraints and the corresponding DFT strategy. They have very specific constraints to deal with. And we'll talk then about the historical flow, so what they have been using for years now. By the way, ST Imaging Division has been a long-time user of Tessent tools. They are doing 10 to 15 tapeouts each year, so it's a lot. And they're today doing all their DFT insertion with Tessent. Then we'll talk about the trials and different configurations that Sara has been running. We'll do a quick look on the results and comparing the different results against different criteria. But that's got to be short. Okay. And then we'll conclude. So let's move on with the presentation of the imaging division. Like I said, it's a very, very important division at ST. It brings a lot of revenue today, if not the most important division. This is why I work with them, basically. They're specialized in developing advanced sensing solutions which are going to different type of products, time of flight sensors, image sensors, and ambient light sensors. These products are applied through wide variety of markets: personal electronics, medical systems, automotive, and industrial. By the way, on the medical and automotive side, they have to comply with some very specific standards, typically ISO 26262, as some of you may know. And on this front, by the way, all the Tessent DFT IPs are certified. So it's not only the software, but also the hardware generated that is completely compliant with the ISO 26262. So that's about the imaging division. Now let's talk about the project constraints and DFT strategy. So these are very specific products, as I was explaining. They are mostly analog mixed signals products. Of course, they have ultra low power constraints, as you can imagine, because they are embedded into other type of devices, bigger device, but the lower power, the better for them. And they are very, very small in size. So typically they can't use the traditional JTAG tap interface. Usually they use the functional pads to bringing, or at least to apply the scan data and do all their manufacturing tests. So what they typically do is that they use I2C as a mechanism to configure all their device, and then the last sequence of I2C let them turn their I/O into test I/Os, or I/Os used for the manufacturing test. So this brings a couple of challenges. Area and low power. Low power, of course, they are using the low power configuration of or at least the low power hardware of our compression logic, which allows to reduce the shift power. They use a lot of clock gators as well to ensure that they lower the power consumed during capture. And finally, in terms of area. They try to minimize as much as possible the area and make sure that they are using this limited number of pads. So typically they use one of our IP, which is called low pin count test. So let me highlight here. LPCT in short. This has been fully developed in partnership with this division, by the way. Now, this technology, by the way, is replaced more and more by the SSN through IJTAG for those who can afford a tap. But still, this remains a very useful feature, basically. The low pin count test basically generates this IP generates all the control signals for the compression. So EDT update, shift capture, clock, or slow shift capture, clock, and so on and so forth. The embedded deterministic test, EDT in short, is of course plan of record as well in all of their device in order to reduce the pattern count and make sure they have a short test time. And they use not the Tessent on-chip clock controller, but their in-house on-chip clock controller, which is also fully supported by the Tessent shell flow. Okay, so these are the different elements that they use, and this allows them to address all the different challenges that you have listed just here. Okay, moving on. So this is a little bit about their traditional flow, historical flow. You should be you should know this kind of diagram that we see with the traditional scan chains in blue here, the decompressor and compactor, and scan channel in and scan channel out. Okay, that should be familiar to everyone, hopefully. What they used to do was a symmetric EDT insertion, symmetric in that there's the same number of channel in and channel out. So here, in this example, we have already 4 I/O ports which are used, which is already a lot. So the only remaining port, if they are using 5 pins to bring in the manufacturing test data, is just an additional pin. This is handled by one of our LPCT IP, basically. So what you see in these slides also illustrate the placement of what we call OCC segments or OCC care bits that you may be familiar with as well. On-chip clock controllers, as you may know already, are used to control the functional the functional clock during at-speed tests, but also brings in the slow test clock, slow shift capture clock. Those OCC care bits usually need to be put into those scan chains, so in those compressed scan chains, because they are part of the compressor-decompressor IP. What we typically recommend to avoid clustering and basically to not reduce the encoding capacity of the EDT IP is to make sure that we don't align in the same shift position the OCC care bits. So we will see how they could play with different configuration, but historically they were placing all these OCC segments in a cascaded way so that you never have the same location, at least the same shift position for each and every OCC segment. Okay? So that's the historical flow. Now, moving on to the different trials and configuration, they first investigated, while talking with us, they realized that we could support what we call asymmetric EDT implementation, where you don't have the same number of channel in than the number of channel out. Okay, so in this case, that was very interesting for them because this allows to reduce the number of pins used. So in this case, we have a configuration with 2 channel in and 1 channel out. That was the first trial. The second trial was the opposite, 1 channel in and 2 channel out. And in that case, in this configuration, we kept the placement of the OCC care bits at the same way they were doing historically. And here are the first results that they could get. So you see in this table The first trial is basically the reference, what they used to do in the past, where we have a symmetric implementation with 2-channel in, 2-channel out, compared to those 2 additional trials with an asymmetric implementation, 2-channel in, 1-channel out, and the opposite. The criteria are the following: test coverage, of course. This is very important to make sure you have a good quality in terms of manufacturing tests. The number of EDT abort faults, so those faults which are not addressed by the ATPG engine when dealing with the compressed patterns, making sure that you don't have a too long runtime, basically. The number of patterns and the total area, very important since those designs are very small. And finally, the runtime. So what we can see in this interesting chart or table is that they could get, actually on this specific design on which they have done the trials, they could get a better coverage with an asymmetric implementation, as to know, with 2-channel in and 1-channel out. The number of EDT abort faults has reduced. They had a little bit of a pattern inflation, 3% more patterns, but that was not too much of a problem because in their design, if you remember, I explained that they were highly dominated with analog mixed signals designs. So basically, you have a big imager on top of the die, which is very long to test. The analog test is usually much longer than the digital test. So it was not a big problem to have a 3% pattern inflation. The total area, however, was reduced by almost 1%. So it's, like I said, in some of their design, every flop count. So it's quite important to have this kind of results. And the runtime in the end was also better. The other asymmetric implementation with 1-channel in and 2-channel out was actually worse. We got less coverage, higher pattern count. Well, I guess a slightly better. Sorry for the color coding here. There's a little. It should have been marked as or colored as green, but it was a little bit better and higher runtime. So definitely, they will try to have to use more of this kind of implementation. Yes, question.
So that was the only change. Reduce the number of. So in the second case, we did just once and output instead of two.
Yep.
Get better result.
So that's a very good question. We've not investigated with engineering why we were ending with such results. Indeed, it is counterintuitive, I would say. Indeed, but indeed, the ATPG engine in this case did a better job with just 1-channel out compared to the symmetric implementation in the end. It was exactly the same. So it's always worth, at least if you are really sensitive to, area and test coverage, it's always worth trying different EDT configuration, basically. The typical chain length that anyone would use, so between 200 and 300 scan flaps per chain.
Would this be a general observation for having less inputs than outputs that is worse, or?
So I would answer with a very generic answer. This is design dependent, but basically yes. I will draw some conclusion on that aspect. Basically, over those different trials, they decided to implement some strategy where they cover as much as possible configuration. But I will go to that point at the end.
Using serializer here.
What do you mean by serializer?
This kind of are they shipping some serial data and then this becomes probably.
It's not pipelined. They are channel in, channel out are not pipelined. It's direct data from the chip level input output, basically. Okay, how am I doing on the time? It's okay. Oh, okay. All right, so let's move to the other trials they've been playing with. So basically, in addition to playing with the EDT channel in, channel out, they wanted also to investigate the placement of OCC care bits. So they've started from this asymmetric implementation that was better, basically, and they tried to first move the care bits, the OCC care bits, into a non-compressed scan chain, so really outside the compression decompression logic. Okay. The drawback with such implementation, of course, at least for them, is that you need to add 2 additional pins to handle this, to provide this data. So that's the drawback. So that was one additional trial they have done. And also they've done another trial where instead of cascading all the OCC bits across those different scan chains, they've just used one single dedicated compressed scan chains to store all the OCC segments, all the OCC care bits. So here are the results. So first of all, we used as a reference the second trial that we have seen just a couple of slides before. So with a reference coverage of 97.61%. So in trial 4 and trial 5, we have these 2 additional configurations where they play with the OCC care bits. So in this case, with the OCC care bits placed into an uncompressed scan chain, and in this other case, where all the OCC care bits are placed into a dedicated compressed scan chain. And so again, what you can see, so this is actually expected. The tool does a much better job because it's less constraints. It's got less constraints on the compression. So when you are using an uncompressed chain for the OCC care bits, you get even better test coverage, 98%. You still get a good coverage and a good improvement, not when you have all your OCC care bits into a dedicated scan chain, compressed scan chain in this case. Again, on the number of test patterns, less patterns in the case of having all the OCC care bits into an uncompressed scan chains, a little bit more patterns in the case of having all the OCC care bits placed into a compressed scan chains, and still very good results in terms of area reduction. So with a little bit of higher runtime in the case of compressed care bits placed into a dedicated a compressed scan chain. Now moving on to the reference where we take as a reference the historical flow with the cascaded placement of the OCC care bits. That way we have a good understanding of how much improvement we could get with both the asymmetric implementation and also all the OCC care bits placed into a compressed scan chain. So you see here the numbers are better. Again, we use some color coding here to highlight the benefits. So in those 2 configurations, we get basically better coverage, a little bit of pattern inversion, but better area in the end. So with the drawback in the case of external OCC that we need to add 2 additional pins. That's it. So it's not applicable to all of their designs, but it's still a very interesting result because we get better coverage in the end. Okay, I think that's it. So let me go to the conclusion slide. I told you it was short and simple. So basically, the takeaways is that for this example design on which they've done all these investigations, definitely the 2 channel in to 1 channel out configuration gave the best results. The OCC bits placement had really a big impact on the results they could get. They were quite surprised with those results, thinking that they had an optimal flow. In the end, we could see, as I was explaining, that this is design dependent, and if you are really caring about coverage and getting those few % more of coverage, and also trying to reduce as much as possible the area while not taking too much care of the pattern count, then it is really needed, or at least it is very useful to to try different type of configuration, different type of OCC cabinet placement. So in the end, those trials open new possibilities for optimization in their implementation. And so in their future approach, what they have applied today is that they have modified all their scripts to test and to browse basically through those different configuration, trying to find early on the best configuration and get advantage of these different techniques. That's it for today. Thank you very much for listening to me.